This set of slides is a short recap of the most important things you should have at your fingertips about simple harmonic motion. This would have been the last chapter covered in Physics 1050. It would not have been covered at all in Physics 1020, and it would have been covered fairly thoroughly in Physics 1021. For anybody who needs a deeper recap of this topic, there's a review section under course contents that has a set of notes and an hour-long video that includes lots of examples about simple harmonic motion.
For simple harmonic motion to happen, we need something that provides what we call a restoring force. So what I have here is a spring and a mass. I'm going to take this mass and hang it off my spring. We know that gravity pulls down on the mass and it makes the spring stretch out. The spring is pulling it up, the earth is pulling it down. So where the mass is right now, and it's not moving, it's in equilibrium, we call this the equilibrium position. If I pull my mass down a little bit, the spring is going to start to pull it back up. It'll move upwards. Once it passes the equilibrium position, the spring is going to push it back down towards the equilibrium. So this spring force always pushes the mass towards that equilibrium position. That results in what we call simple harmonic motion.
Okay, let's get some definitions and some diagrams and some equations to go with that short video we just watched. So we take a spring and we put it on a hook. The spring is at its equilibrium length. It's not stretched at all. Then the next thing we do in our next step is we attach a mass to the spring. When we attach the mass, the spring stretches down because the earth pulls down on the mass. Stretches down by some distance y. So y is the amount of stretch. Okay, what happens here? Well, that mass will come to rest at this new position if we release it very gently. So we could draw a line along where it comes to rest. This line represents the new equilibrium position. So equilibrium position. Traditionally, we say the equilibrium position has y equals 0. It doesn't have to be equal to 0, it's just like picking an origin, but it's most convenient to pick 0. Since the mass is in equilibrium, it tells us that the net force acting on the mass is equal to 0 because it's in equilibrium. So since we've mentioned forces, let's draw a free body diagram. We have the Earth pulling down on the mass, that's the force due to gravity. And we have the spring pulling up on the mass. That's the spring force, which is given by Hooke's law. So Fs stands for spring force. Okay, let's write down our Newton's second law expression. Sum of the forces in the y direction is mass times acceleration in the y. That's our general expression. We have the spring force that points up. We have the force due to gravity, which points down, so it's negative. And because the mass is in equilibrium, the acceleration is 0. For spring force, we know that Hooke's law says that the spring force has a magnitude of k times x, where k is the spring constant and x is the amount of the stretch. And the direction of the spring force is opposite to the displacement relative to equilibrium. Okay, so our spring force points up, it's positive. It's equal to k times the stretch. You're used to seeing that as an x, but we can call it a y since we decided to call our stretch equal to y. Force due to gravity is m times g. That's equal to 0. So in our table, spring constant is equal to k. Okay, so that's what's going on at equilibrium. K times y is equal to m times g. You know, in an experimental setup, if you knew the mass, you could measure how much it stretched and you could calculate the spring constant. Okay, next, what happens if we take our mass and we push it up a little bit? Let's call that little bit we push it up by a. So what if we push it up by some distance a? And then we let it go. Well, what happens is it starts to oscillate up and down. The maximum distance it can have from equilibrium is that distance a. So if we push it up by 2 centimeters relative to equilibrium, the highest above equilibrium it could be is 2 centimeters, and the furthest below equilibrium it could be is 2 centimeters. So that's the furthest it could ever be from equilibrium. So that A that we pushed it up by, we call that the amplitude of the motion. That's the maximum distance from the equilibrium. Usually that's measured in meters. Spring constant is newtons per meter. Amount of stretch is meters. Force is newtons. Okay, and our equilibrium is the center of oscillation where the net force is 0. That was where y was equal to 0. So how can we talk about that oscillation? Well, one thing that's important to ask about that oscillation is how long does it take for one complete oscillation? So if it starts at the top, one oscillation would be where it goes down to the lowest point and comes back up. That's one complete oscillation. The time for one complete oscillation is called the period. That has a symbol of t, and it has units of seconds. Another way we characterize these oscillations is by asking how many times does it oscillate in 1 second. That's called the frequency, and that has a symbol of f. The units of frequency are either seconds to the -1 or hertz, H-E-R-T-Z, with a symbol of Hz. Since period is the time for one oscillation, or the number of seconds per oscillation, frequency is the number of oscillations per second, frequency is 1 over the period. Okay, so that's a quick recap of everything we talked about in that video and how we characterize the oscillation. Okay, let's start by trying to get a mathematical description of simple harmonic motion. That means let's find the equation for x for position of the mass as a function of time. Let's start with a mass on a smooth horizontal surface. The equilibrium position is where x is equal to 0. That's the center of the oscillation. That's the place where the net force is equal to 0. And then we'll have that the mass can be pulled out to some distance equal to the amplitude. When we do that, when we pull it to the right of equilibrium, there's a spring force that pulls it to the left. So we can draw a free body diagram just by putting that force on there, and here's our mass M. Okay, we don't draw a friction on here because we're saying it's a smooth surface. Let's apply Newton's second law in the x direction, in the horizontal direction, to our mass on the spring. So the sum of the forces in the x direction is mass times acceleration in the x direction. The only force is the spring force. It points left, so we have minus kx. K is the spring constant. X is the amount it's stretched by relative to equilibrium, equals mass times acceleration. To solve this equation, you have to simplify a bit. If you remember, velocity is the derivative of x with respect to time, and acceleration is the derivative of velocity with respect to time. That means it's the derivative of position with respect to time, which means it's the second derivative of position with respect to time. I'm going to pop that into my Newton's second law expression. Minus kx equals mass times d2x dt2. I'm going to divide both sides by mass to get the second derivative of position with respect to time is minus k over m times our position x. Now, when we have an equation with this form, we know that the solution to this equation is x as a function of time. So the brackets doesn't mean position times time. It means position depends on time. So x as a function of time is equal to a, that's the maximum distance it can be, or the amplitude, times cosine of omega times t, where omega is equal to the square root of k over m. So this is a math thing to solve this equation. If you wish, you can go ahead and prove to yourself that it's true. If you take the second derivative of this expression right here, if you take the derivative twice, you should see that it works out to be minus k over m times x. That might be a useful exercise for you to try. One last thing we could do is we could make a plot of this, and we could ask what's happening over time. So when we take our mass and we hold it at the amplitude, if we release it, then initially the velocity is 0 and it's going to move towards the left. So it starts at a big position at the amplitude with a velocity of 0 and moves left. So initially it goes like this. It speeds up as it goes because there's a force pulling it to the left. As it passes the equilibrium, x equals 0, that's when it's going to start to slow down as it continues to move left. It'll keep going left until it gets to the negative amplitude, at which point the force is still going to be to the right, but it's going to speed it up as it keeps going back towards the equilibrium. And that's just going to repeat over and over. So if you draw a graph of x versus t, you'll get that cosine form. So where x is equal to the amplitude, the velocity is equal to 0. Where x is equal to 0 at the equilibrium, the velocity is equal to a maximum. So let's just think about that graph a tiny bit more. So our oscillator will go back and forth between the amplitude and the negative amplitude, so as far to the right to as far to the left, back and forth the whole time. The shape of the graph goes like a cosine. So sometimes it could be at the amplitude, and an amount of time later it will be back at the amplitude. That amount of time is called the period. So that's one complete oscillation. From the amplitude back to the amplitude is one full cycle, and that takes an amount of time equal to t, the period. Okay, that's not the only place we could draw a period. It could also be from the lowest point, or the leftmost point, back to the leftmost point. So this is also one full oscillation. Okay, so that's a full oscillation which takes time t as well. Let's see if we can layer that in our equation for x. So from our previous slide, we said that x of t is equal to the amplitude times cosine of omega t, where omega is root k over m. K is the spring constant and m is the mass on the spring. However, we can also write, because cosine is a periodic function and it repeats with some characteristic time length, we could also say that x is equal to cosine times 2 pi over that characteristic time of the period times t. These are both identical ways to describe the graph we have here. So what this tells us is that omega must be the same thing as 2 pi over t, which is the square root of k over m. Then the other little bit we can layer in is that frequency is 1 over the period. So that's the same thing as 2 pi f. That's a pretty important result. Should always keep that one handy. What other thing will I mention while we're on this slide? If you're ever calculating these values on your calculator, then 2 pi implies that we're in radians. Your calculator always has to be in radians mode. So that's an important tip that you might want to keep in mind. So we've already established the equation for position. X is equal to A times cosine omega t, where omega equals root k over m. It's the angular frequency, or the cycles per second in radians. And then x oscillates between a maximum value of plus the amplitude and a minimum value of minus the amplitude. So x goes back and forth between plus and minus a. Our initial condition that we have here, at t equals 0, x is equal to the amplitude, and the velocity v, of course velocity is the slope of a position versus time graph, is equal to 0. Okay, that's our initial condition. So if we wanted to find our velocity equation, we would remember that velocity as a function of time is the derivative of x with respect to time t. So we've got to take the derivative with respect to time of a times cosine omega t. To take this derivative, we can take our amplitude a outside because it's a constant. We've got d by dt of cosine omega t. So that's equal to the amplitude. The derivative of cosine is minus sine with the same argument, omega t. Then you have to multiply by the derivative of the argument, which is omega. So v as a function of time is minus a times omega times sine of omega t. Here's the equation for velocity as a function of time. What do we notice about this here? Well, our position graph has a period of t. That's tied into our omega because omega is root k over m. It's also 2 pi over the characteristic time t. We see that our velocity graph has the same omega, so it must have the same period. Let's label that on our picture. So the amount of time to go from a maximum back to a maximum is exactly the same. What about those maximum? Would that be the same or different? Well, it kind of has to be different. Our maximum position is given in meters. Our maximum velocity is given in meters per second. Those two things can't be the same. Let's think about what those maximum are. So there's the maximum, there's the minimum. So if we wanted to get a maximum velocity, what would we have to have for our sine term? So if we want v to be the biggest, if we want this to be the biggest, what do we have to have for our sine term here? If you think about your trig functions, then sine oscillates between two values. It goes between plus and minus 1. If we want v to be the biggest, we have a minus here, I would argue that sine omega t has to be equal to minus 1. So v is maximum, it's the very biggest, if sine omega t equals minus 1. That means that v maximum would be minus a omega times minus 1 equals a omega. So this a omega is our max velocity. So we can put that in our picture. A omega and minus a omega for the smallest or biggest negative, maybe you would say. Okay, what about acceleration? Well, acceleration is the derivative of velocity. So acceleration as a function of time is d by dt of the velocity as a function of time. So that's going to be d by dt of minus a omega times sine omega t. That derivative is going to be minus a omega. They can come out front. Derivative of sine is cosine omega t. Then you multiply by the argument, so we get another omega there. So our expression for acceleration is minus a omega squared cosine omega t. Okay, here, what are we interested in? We've got that same omega, so acceleration has the same period as velocity and position. So all three of those things have exactly the same period. Our maximum acceleration would occur if cosine omega t is equal to minus 1. So our maximum acceleration is a omega squared. And the last thing you can show is that the acceleration as a function of time is minus omega squared times x of t. So if you look at your acceleration equation, you've got minus a omega squared times cos omega t, but a times cos omega t, that's the same thing as x. So acceleration is the same as minus omega squared times position. We're just about done now. The last thing we have to do is just talk about that starting point. In the graphs we've had so far, x has always started at the amplitude. We've always started our stopwatch when x is at the biggest possible value. But does that have to be true? I would argue that it doesn't. You could turn on your stopwatch anytime you wanted to, but it would still be the same oscillation. So let's think about what happens if our initial position, x of 0, is less than the amplitude, because you're totally allowed to have that. So then our equation of motion needs to account for the fact that we don't start at the amplitude. The way we do that is we introduce what's called a phase constant. Position as a function of time is equal to the amplitude times cosine of omega t plus phi. So this phi, this term here, it's an angle in radians, and that allows for an oscillation to start someplace other than the amplitude. So phi is called the phase constant. Let's just give that a test. What happens at t equals 0? So at t equals 0, our initial point, x of 0, so x at t equals 0 is equal to a times cosine of omega times 0 plus phi equals a times cosine phi. And since cosine of some number is going to give us a value less than 1, it means that our initial position x is less than the amplitude a. So that phase constant allows us to have a starting point other than at the amplitude. Then for our velocity, v of t, that would be minus a omega sine of omega t plus phi. And our acceleration, a of t, would be minus a omega squared times cosine omega t plus phi. You get those equations in exactly the same way by doing the derivatives. The only difference is we have that phase constant inside the argument now. So that was a pretty quick recap for you. Here's a summary slide. This has been included in the slides in other places, but here's everything on the one page. If you're looking for some more information, this is from chapter 14 of your textbook. You can also check out the review topics under course contents. I've published a Mastering Physics assignment for you. It's not worth any points, it's just there for credit, but if you want to make sure you got it, you might want to go through those as a little bit of homework. Under the course contents, the review topics, there are notes and some video links, and then there are some extra example problems on the YouTube channel. If you do a search for Shoreland Physics, my channel should be the first hit.